Hey guys, this is Mr. Wolf. I'm going to be starting the second video of our lecture today, and it's going to be looking at the second part of Target 3, which is the law of conservation of energy. So if you guys go to page 14 of your packet to start writing your notes for this, we're going to be jumping around from the back of the packet to this part. But starting on page 14, the law of conservation of energy states that energy cannot be created or destroyed, but it can be transformed, right, from one form to another. But the total amount of energy, right, will never change. And so an example of this is we have potential energy, right, in our bow when we lift it. Right, when it's released, that potential energy is going to be gone, but it's not destroyed. Right? It's not going to be destroyed. Instead, it is just transformed into another type of energy. In this case, it's going to be transformed to kinetic energy, because our arrow is going to be in motion, and kinetic energy is energy in motion. Right. So what I want you guys to do is now flip to the back of your packet. Hopefully you guys have some room left to write this, but I'm going to create another example of our system for you guys. And remember, we have our system, but we likened it to and you know what, I'm going to just draw a new box just because I want to be able to write some stuff on the side. For you guys should still be fine. So here's our system. All right, we're likening it to a bank. And remember, before, you could have the money in your account be in cash or savings. Right. And so let's say I have $500 in cash, $500 in savings. Right? That's going to equal a total amount of money of $1,000 in my bank. Right? Now I could switch this money around. It could basically, the money in my account of $1,000 here could basically transform from my savings to cash. Right? So let's say I want to put some money away. I could put some of that cash into savings. Well, let's say now I have $800 in my savings and $200 in cash. Right? The money in my account has not changed. It's still it's $1,000 in my account. And let's say I want to go on vacation, so I want to have some available cash. I'm going to have $700 in my account and $300 in savings. And still have that total amount of cash in my account being $1,000. It's just changed forms from cash to savings. Well, the exact same thing is going to happen with our system for energy. Remember, we liken cash to kinetic energy and savings to potential energy. It's going to be the exact same thing. And so instead of having 1,000 joules in my system, we're going to have $1,000 in my system. We're now going to have 1,000 joules. So I'll get rid of that here. And so the kinetic energy and potential energy could just have different numbers. We could have basically potential energy that transforms into kinetic energy that transforms into potential energy, but the energy of the system is going to stay the same. Right? Energy cannot be created nor destroyed. Now, one thing I did want to state, and you guys don't have to draw this before the image went away, is that we've been talking about energy in our system changing, and that's when we do work on our system, whether we're taking energy away or out, and that's true. So we could change the amount of energy in our system, right? But that system might just be an object. If we were to expand our system and continue to keep on expanding our system, the total energy within our system would remain the same. And so eventually, when we expand to the entire universe, what we found is that energy is not created, nor is it destroyed. Right, so for this, let's look at an example of a woman jumping from a building that's on fire, right, into the trampoline right here. So our total mechanical energy, and just a review from that first video, the total mechanical energy is just going to be the kinetic energy plus potential energy. And what the law of conservation energy states is that basically, unless we're doing work in our system, this is going to remain the same. And so here, our total mechanical energy is going to be 10,000 joules. Sorry, the zero's not written the best. And as she falls, she's losing height. All right, and so her potential energy is going to go down, but she's gaining speed. So her kinetic energy is going to be increasing. All right, but the total mechanical energy of our system is still going to be 10,000 joules. Same here. She's decreased in height. She's increasing speed, so she has more kinetic energy, but we add them up, it's still going to be 10,000 joules until we get to the very end right here. This is basically a split second before she hits that trampoline, where basically all of our energy is now in the form of kinetic energy, and we basically have 0 joules worth of potential energy. Now, once she makes contact with the trampoline, she's going to be applying, there's going to be some type of force there, right? And so if we have some type of force, there's going to be some type of work going on here. And so energy is going to be entering or leaving our system. But when our system is isolated during this time, right, the total energy of the system remains the same. Energy is simply transformed between kinetic and potential energy. Right. So when you're setting up these problems, take these steps for the conservation of energy problems. First, just draw your scenario. Sometimes I could just be basically drawing something at a height, labeling where the object is, what the height is, and anything else you need to know in terms of mass or anything else. All right. And then you're going to make a chart using height, kinetic energy, gravitational potential energy, and total mechanical energy. And I'll show you that chart in just a sec. It's on the next page. And then you're finally going to solve using our equations right here. All right? All right, guys, so I'm actually not sure. My video, I think, just paused. So where we're at is pages 14 and 15. For this next problem. So the problem or the question starts on the bottom of page 14, but we're going to be doing the work on page 15. And so if you could pause the video to look at the word problem and what it's asking for A and B. And here's the picture we would draw right here. All right. And so that's our first step. Our second step is to make the chart for height, kinetic energy, gravitational potential energy, and our total mechanical energy. I don't know why there isn't an M there. So at the height of 6 meters, our can is basically sitting on our scaffold. So it's really not in motion, so we have a kinetic energy of 0 joules. All right, so that means we have to find the gravitational potential energy now. Right, and we know the equation for that is going to be mgh. All right, so we could do 1.5 times 9.8 times 6, and that's going to give us energy of 8.2 joules for our potential energy. All right. We know that the total mechanical energy is equal to the kinetic energy plus our potential energy. So it's just going to be 88.2 joules. All right, now it's asking for number A is what is the kinetic energy of the can when it is at 4 meters, right here. Right. Well, we know that energy within our isolated system has to remain the same, that total mechanical energy of 88.2 joules. Right? But we've gone down in height, so our gravitational potential energy is going to differ. So we're going to use this equation right here. Total mechanical energy is equal to kinetic energy plus potential energy. We have 88.2 here is equal to our kinetic energy plus, and I'm going to use my equation for potential energy now, which is mgh. So 88.2 is equal to my kinetic energy plus the mass of my can times gravity. Sorry, I can't fit it in here at the edge of the PowerPoint, but the height I'm bringing down here is going to be 4 meters. All right, and it's going to give us 88.2 equal to kinetic energy plus 58.8. We're going to get a kinetic energy of 29.4. And I haven't put it in the box yet, but we solved for the potential energy. That's going to be 58.8. All right, and this is all in joules. It's just tough for me to write in these boxes. I apologize. All right, so for A, it asks what's the kinetic energy they can at 4 meters. We found that right here, 29.4 joules for A. All right, it then asks, what is the speed of the can basically right when it hits the ground? So I'm going to clear this up here. All right, I'm going to add a couple numbers that we had before here. 88.2, 88.2. Okay, and we know that our total mechanical energy of our system has to remain at 88.2 joules. All right, so I'm going to set this up again. Total mechanical energy is equal to kinetic energy plus potential energy. So we have 88.2 here. And here, our potential energy, right as it hits the ground, we could treat it basically as 0. And so we're going to have all our energy be in the form. It's going to all be transformed into kinetic energy. So that's also going to equal 88.2 joules. All right, but it's not asking for the kinetic energy. It's asking for that velocity. So we have to look at our equation for kinetic energy, which is 1/2 mv squared. Okay, we have the variable that we want in this equation, so let's solve for it. 88.2 is equal to 1/2, 1.5, and then v squared. Right. When we solve for v algebraically, we're going to get 8.13 meters per second squared. Right. Since velocity is a vector, we know we're going downward, so there should be a negative 8.13 meters per second squared. Right. So this concludes it for the video and really for the lecture for today. Sorry about some of the messiness with just writing with the PowerPoint. Hopefully you guys were able to get this. Please ask me any questions tomorrow if you have any, and I'll see you guys later. Bye.